Welcome back. In this video, we'll practice using parameters to describe solutions to linear systems. We'll also define the general and particular solutions to a linear system. In this example, we need to describe the solution to each linear system using parameters. Notice that in both parts 1 and 2, the augmented matrix of the linear system has already been reduced for us. In order to assign parameters, we need to remember the convention from last time. The convention says that we should assign a parameter to any variable that isn't associated to a leading entry. This means that once we have the row echelon form or the reduced row echelon form of an augmented matrix, we should identify the leading entries. In example 1, I only have one leading entry in the first row. That means that the variable x is associated to a leading entry, but the variable y is not associated to the leading entry. Because of this, we should assign a parameter to the variable y. And remember, we have to think about that t could be any real number. Once we've assigned a parameter to the variable y, we can go back and we can see what information row 1 tells us about the linear system. So here, row 1 says that x minus y is equal to 1. That's the same thing as x is equal to 1 plus y. But wait, we know that y is actually equal to t, so I'll rewrite x is equal to 1 plus t. Finally, we can put this solution in parametric form as x equal to 1 plus t and y is equal to t in R. We need to go through the same procedure with the second example. The first thing I do is I identify the leading entries. In the first row, the leading entry is 1. In the second row, the leading entry is 1. And in the third row, there are no leading entries. Now let's look at the variables associated with this linear system. I can see that there's 4 columns to the left of the solid line, so that must mean 4 variables. I have variable x1, x2, x3, and x4. I can see that both the variables x2 and x3 are not associated to leading entries. This means that I should assign a parameter for each of them. I'll say that x2 is equal to s and x3 is equal to t. Here, now both s and t are varying over all real numbers. I can go back and I can read off the rows. Row 1 tells me that x1 minus x3 is equal to 3, which is the same thing as x1 is equal to 3 plus x3. And from row 2, I have that x4 is equal to 2. Now that I know the solution to the linear system, I can get organized. I have x1 is equal to 3 plus x3, which is really t. x2 is equal to s. x3 is equal to t. And x4 is equal to 2. S and t are going to vary over all real numbers. In example 3.2.9, we'll solve the linear system with the two equations x plus y plus z is equal to minus 1 and x plus 2y plus 3z is equal to minus 4. Like usual, first I have to write down the augmented matrix of the linear system by keeping track of the coefficients and constants. From the first equation, I have 1, 1, 1, and minus 1. And from the second equation, I have 1, 2, 3, and minus 4. I already have a 1 in the top left position, so I'll use that 1 to clear below using the elementary row operation. Row 2 minus row 1 becomes the new row 2. When I do this, the first row stays the same. And the second row, I have 1 minus 1, which is 0, 2 minus 1, which is 1, 3 minus 1, which is 2, and minus 4 minus minus 1, which is minus 3. The matrix at this stage is in echelon form. I'll go for reduced row echelon form by using the leading entry in the second row to clear above it. With the elementary row operation, row 1 minus row 2 becomes the new row 1. Here, I have 1, 0, minus 1, 2, and 0, 1, 2, minus 3. Okay, at this stage, we can identify the leading entries, 1 and 1. Notice that the variable x has a leading entry, the variable y has a leading entry, and the variable z does not have a leading entry. Therefore, we'll assign the parameter t to the variable z. Once I've assigned the parameter t, I can start looking at what the rows of the matrix tell me about the linear system. From row 2, I have that y plus twice z is equal to minus 3. That's the same thing as y is equal to minus 3 minus 2z, but z is t, so we'll write it in this way. From the first row, I have that x minus z is equal to 2, but that's the same thing as x is equal to 2 plus z, z is t, I'll write it as 2 plus t. Organizing my answer, I have x is equal to 2 plus t, y is equal to minus 3 minus 2t, and z is equal to t. T is any real number. Let's now define the general and particular solutions of a linear system. If a linear system has infinitely many solutions, the general solution is the parametric or vector equation that describes all possible solutions. A particular solution is one numerical solution. So when we look back at the previous example, we can see that we've already written down in parametric form the general solution. To find a particular solution, we can pick any t value we like. I usually like to pick t equal to 0 because it's easy to deal with. When I do that, I get that x is equal to 2, y is equal to minus 3, and z is equal to 0, giving me the point 2, minus 3, 0. It's important to remember that this is a particular solution and that there are actually infinitely many particular solutions. For each t value, you get a different particular solution.